Hey guys, guess what? This is the third time that I've tried to get this out to you because people keep calling overhead. So just pay attention. And if you hear somebody call with the intercom, I'm just going to roll with it. Okay, how's that sound? So we're going to look at exponential growth and we're going to talk about this. This is a little bit different than the linear growth that we've been doing. And if you'll pause for a minute and just read this letter, and then move on to the next slide, we'll be able to go on. So go ahead and hit pause and then come back to me in just a moment. All right, welcome back. Would you be likely to try this scheme? Probably because you think you're only going to spend $20, right? And it's going to keep going on the Energizer Bunny. So let's think about this for just a minute though. And if you were first on the list, you would get 2 times 10 to the first power, or you would get $20. If you were second on the list, you would get 2 times 10 raised to the power of 2 because each friend would have 10 friends, and that's 200. Notice the pattern, 2 times 10 to the power of 3. And so 10th on the list would be 2 times 10 raised to the power of 10. So that would be a 2 and a 0, and 0, 0, 0, 0, 0, 0, 0, 0, 0. So by the time you were the 10th person on the list, you would end up with $20 billion. Okay? So if we're going to talk about writing the function and talking about each part of the function, well, f of x, the original amount is $2 multiplied by a rate, or 10, and raised to the power of x. So let's take a look at this one. If letters like this circulated in a city of 100,000 people, what do you think would happen? Well, a couple of things would happen. Somebody would break the chain, right? That's why they're called chain letters. They wouldn't finish it, and of course, then nobody would get their money, or you'd eventually run out of people. I want you to pause for a minute and just jot yourself a note for number 5, and then also sketch a graph for this, and we'll look at this tomorrow when we walk in the door, okay? All right, so let's take a look at this. We're going to talk about exponential growth and decay, and right now, the way that you can tell that this is exponential is because x is being used as the exponent, okay? So if Mrs. Rose were just to make a table of this, and let's make it an expanded table to make life a little bit simpler, and let's say we start with negative 2. Well, that would be 3 to the negative 2 power. Okay, so that means reciprocal power raised to 3 squared, so that would be 9. Negative 1 would be 3 to the negative first. That would be 1/3. 0, well, any non-zero number to the 0 power is, thank you, that's 1. 1, 3 to the first, of course, is 3. And 2, 3 to the second power is 9. That's the tabular data. Now, what if Mrs. Rose wanted to put this in graphic representation? Well, if Mrs. Rose were to put this in graphic representation, it would go here, and it's easy. Let's get a pen here, Mrs. Rose. If Mrs. Rose looks at this and she calls this 1, 2, 3, 4, 5, 6, 7, 8, 9, and this is, of course, 1, 2, 3, and of course, negative 1, negative 2, negative 3. At 0, we would be at 1. At 1, we would be at 3. At 2, we would be at 1, 2, 3, 4, 5, 6, 7, 8. Oops, let's go. 1, 2, 3, 4, 5, 6, 7, 8. And of course, we'd be at 9. And here we'd be at about 1/3. And here we'd be at 1/9. And guys, it's kind of like matter cannot be created or destroyed. We're never going to cross this 0. It's going to get closer and closer to 0. This is a boundary line, and this is called an asymptote. Okay? That's something that you always approach, but you never cross. And you're going to learn more about that in calculus next year. But notice that this is a curve. It only goes in the first and second quadrant. And notice that the rate of change changes. It's not a constant rate of change. See? It's not a constant rate of change. and that is because x is being used as an exponent. So let's take a look at this one, and let's think about what would happen here, okay? I'm not worried so much about the graph right now because, of course, graphing this would be absolutely absurd. But let's think about a tabular, shall we, for just a moment? Yes, Mrs. Rose, we shall. So let's go with x, and then, of course, 40 times 4 raised to the power of x, and let's go to y, okay? And so let's think about this for a minute. If I have this as negative 2, this would be 40 times 1/16. So that would be 40/16. Both of those are divisible by, that's right, 8. So this is 5/2. Let's try another one, negative 1. This would be 40 times 1/4. Okay, so that, of course, would be 10. Notice how fast we jumped. 0, 40 times 1, oh my goodness, that's 40. 1, 40 times 4, that's 160. Notice how quickly this is jumping. 640. Wow, this one really is skyrocketing, isn't it? This is an example of exponential growth. This is an example of exponential growth. You are growing exponentially. It is not a constant rate of change. All right, for some reason. So, when are we going to hear a lot about this? Well, we're going to learn a lot when it's between simple and compound interest. Simple interest is something that you've talked about in the past, okay? But compound interest, ladies and gentlemen, Mrs. Rose would really, 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 really like you to put this as a card in your glossary. Simple interest, of course, is interest equals, that's right, PRT, and time is in years. That is simple interest. We don't care about simple interest, people, because the world deals with compound interest. And we will talk about compound interest in class tomorrow, but really and truly, I want this formula to be in your glossary. So go ahead and put this into your glossary, and we'll talk about this tomorrow. All right, so she receives $200 on her 10th birthday. If she saves it in a bank with 7.5% interest compounded yearly, how much money will she have in the bank by her 21st year? Mrs. Rose, I guess this is where we have to use that formula. The amount that she will have in her account is equal to her principal times 1 plus the rate divided by n multiplied by nt. Now, ladies and gentlemen, here's a hint. N is if it is not equal to the 1 year, okay? If it's equal to the 1 year, then guess what? These can disappear. So let's see. The amount would be equal to, what was her principal? How much money did she put in? 200. This is a growth, 1 plus her rate of 0.075 raised to the power of how many years will she have in it? 11 years, okay? So now that means the amount is equal to 200 times 1.075 raised to the power of 11, okay? How about you use a calculator and find out how much that is and let me know in class tomorrow. All right, what about this problem? Juan and Michelle each have $800. Juan plans to invest $200 for each of the next 4 years, while Michelle plans to invest all $800 now. Both accounts pay 3% annual interest compounded monthly. Will they have the same amount of money after 4 years? If not, explain why. Let's talk about Michelle. Michelle's amount will equal $800 times 1 plus 0.03 divided by compounded monthly. How many months is that? 12 raised to the power of 12 times 4. Okay, there's Michelle. What about Juan? What about Juan? Well, Juan's a little bit different, isn't he? For some reason, this isn't working. Let's think about this. For Juan, he has his first year, okay? And his first amount would be 200 times 1 plus 0.03 divided by 12 raised to the power of what? 12 times 1, correct? That's how much he has in the first year. What about the second year? What about the second year? The second year would be the amount is equal to 200 plus the amount that he has at the end of the first year times 1 plus 0.03 divided by 12 raised to the power of 12 times 1. See where I'm going with this? What about the third year? That's right, 200 plus the amount in the second year times 1 plus 0.03 divided by 12 raised to the power of 12 times 1. And finally, the fourth year, 200 plus a 3, 1 plus 0.03 divided by 12 times 12, raised to the power of 12 times 1. Okay, ladies and gentlemen, that's an awful lot to think about today, isn't it? So how about this? Toodles. Wrap your head around the ones that I asked you to complete and come in tomorrow with tons of questions. Have a great green and gold night. I will see you tomorrow.